Yeah, very bad. Pointer is here. This is your hand. It just takes a second sometimes to get caught up, so don't panic and think that it's not moving a lot of times. That's why people you see jumping between, because they're a little ahead of the game. So, good morning. We're back. It is roughly 10:50, so we will try to get started and stay on our slightly altered schedule. So our next speaker this morning is Ed Malley, who is Vice President at TRC Solutions, and this is one of the presentations that I've been most looking forward to, given what is going on in my state with regard to transforming aging power plants, performance metrics, best practices, and lessons learned. And so with that, I will turn it over to Ed.
Well, yeah. Good morning, everyone, and thanks for being with us today. I really admire all the hard work that the other presenters have put into their products and services and keeping the coal fleet running. Not all coal plants will survive this, and I'm going to talk about the ones that are being decommissioned, retrofitted, closed, sold for other purposes, and so on and so forth. Just a word about TRC. TRC is a energy and environmental engineering and construction management company, publicly traded, about $450 million in sales. Most of our revenue comes from energy clients, financially stable. I'm about as patient as the other presenters are. So, we tend to be located in the Northeast, the West Coast, Texas, and we're filling in the upper Midwest and Southeast with some acquisitions. 3,000 people. Mission, vision, and values. Always safety is number one. I'm going to skip over the rest of this in the interest of time. And get to announced retirements of power plants. So virtually every state in the country has got some closures. These markets started on the West Coast and on the East Coast and in Texas, where there were oil burners. Economics is a major driver. Oils are more expensive than coal or gas, so the oil plants got closed, tended to be closed first. The market is 150 sites. More or less. That number has stayed constant over the last 2 or 3 years. 500 units, so a unit is a boiler and a turbine. A site is a site. If you use EPRI's decommissioning numbers, 15 to 20 million a site, it's a $2 billion market, which means it will cost the utilities or the owners of those plants something like that to get through the process of decommissioning, should they do that. Economic drivers are gas prices and heat rate. The heat rate in a coal-fired power plant is 10 or 11,000 BTUs a kilowatt hour. I think Siemens turbine is down below 7,000. So there's technology drivers, there's a cheap gas driver, and there's, of course, regulatory drivers, which we have tended to focus on. But the thing that's causing these plant closures is cash. As a friend of mine likes to say, the answer is cash. What was the question? The peak closure years, and by closure I mean shutting plants down, likely to be 2015-16, coincident with the MAT's deadlines for compliance. And all these plant closures are a major driver of transmission projects throughout the footprints that they serve. Just a word on reserve margins. A lot of discussion, what are we going to do without the 35 or 50 or 70 gigawatts of power? Reserve margins are pretty significant in most regions of the country, with the exception of California, Texas, and New York. When all the coal plants close, gas goes into curtailment, greenhouse gas kicks in, these numbers are going to change. But right now, the reserve margins are significant, with the exception of California, Texas, and New York. Transmission system impacts. This is not the perfect slide for this, but transmission flows around the country, they tend to flow from certain regions of the country have more power plants and others have less. I tend to think that this map will change a lot when coal plants close. But the points are that taking a node off a grid causes system impacts. NERC does reliability reviews. In some cases, they'll issue a reliability must-run determination. They can't make operators continue to run these plants, but they can give them capacity payments to induce them to run until the reliability issues are addressed. Transmission companies and ISOs act accordingly. So we do a lot of transmission work for investor-owned utilities, and every once in a while they'll complain, oh my, such and such a plant is closing. We have to spend $100 million to upgrade the grid so that the customers have reliable service. Polar vortex. So I had the good fortune to be on a plane from New York to D.C. to Columbus and back to Philly during the polar vortex, and every single one of these old oil burners or coal plants was running, and running hard. So, and of course, after the rules kick in, they may not be able to do that. So people say, well, what's going to happen? There were planned outages of something like 35 gigawatts of capacity that could have been running, but they had planned closures, so they were not running at that time. So that's probably a good thing. The capacity was out there; it just wasn't available at that time. That could be solved by better planning. Gas curtailment. That's a tough issue. If residences need the gas to stay warm, how do you get gas to power plants if the residents are using all the capacity? That's a gas pipeline and storage issue. The utility markets and the commodity markets, gas went from $3 or $4 or $5 up to $100. Now there was a cap of something like $20, and people were in the market said, well, they can't go through the cap, and the traders said, you want the gas? It's $100. You don't want the gas? It's not. Don't take it. So that's another issue to be addressed in the financial markets, and there is but after all this, the bulk power system was pretty stable. There is a NERC report out on this. If anybody's interested in it, it's available on the web. I can get you a copy if you're interested. Just let me know. Reserve margins were very slim, and there's a utility in Ohio that says, hey, we were down to 500 megawatts of reserve margin, and that was it. After that, we were going to have rolling brownouts, blackouts. So this is a serious issue. You can't say it's not going to happen again. It could happen in the summer. It could happen in the winter. But there's work to be done there. 111D rules we've heard a lot about. I'm going to skip over this slide. And I want to talk about our repower initiative. So TRC has been in this market of transforming aging power plant sites since about 2001. We entered into a contract with Con Edison to close a plant in New York City. It was really a real estate deal as part of a big insurance contract, and that was the first one we did. It was a great project for everybody. It was a big real estate transaction. It was a big contract for us. There was development on the back end of it, so all the pieces fell into place. And since that time, we have done 22 projects in one form or another. 15 as an owner's engineer, 5 as a prime. One of them was interesting. It was a mercury boiler up in Connecticut. Those are all finished. There's a whole other series of projects where we're acting as the owner's engineer. Some of them are in progress. Some of them are new. We tend to package the deliverables into 3 or 4 different buckets. The first deliverable we call a playbook. Other people might call it a basic engineering package or a front-end package, but what we try to do is get the existing information that the owners have into an organized format so they know what they have, and then we'll go through an analysis and give them scope of work, cost estimate, schedule for reasonable scenarios that the clients might be interested in, and that can be done in 2 or 3 months, and the results are useful for decision making. The next bucket is effectively a bid package: asbestos survey, hazmat survey, plans and specs, permits, and construction support services on the back end of that. And then for the right project, if the owner's interested and it makes sense for us, we can act as a prime. We have working relationships with, of course, usually our customer is an investor-owned utility, an independent power producer, and then we've gotten to know the asset recovery people, the abatement and demo contractors across the country. So goals, it's always good to have goals when you start a project. Safety is, of course, number one. The safety incident the whole point of this is to remove a risk, a safety risk, a vandalism risk, a financial risk for the various stakeholders. And having a safety incident on a project like this is just a killer. And I mean, literally, it's just devastating to a project. So what we've done is we've developed a health and safety plan, updated through job safety analyses, and one of our clients has asked us to use another technique which is which is required in the process industry. It's called the process hazards analysis. So you go through a what if analysis that's analogous to a PHA under OSHA, and we found it to be a very powerful tool. And we do that at the inception of the abatement and demolition contract with the owner, with the contractor, with the engineer, and other people who are on site. But we found that to be very, very useful. Second thing is environmental excellence. Here again, you're trying to remove asbestos hazards, lead hazards, PCB hazards. So there's really no excuse for spills and other incidents on sites like this. Compliance with law and regulation, and then also maximizing beneficial reuse of building materials, copper, steel, concrete, filling up the basement, and so on and so forth. Costs, there's a lot of cost factors in no particular order. Maximizing asset recovery, both the building materials, the salvage equipment, the real estate is usually the biggest asset. Controlling carry costs and decommissioning costs. One of our clients has approached this as a program, and what they have found is that there are costs spread all over the place. There's costs in the tax department, there's costs in the real estate department, there's costs in the health and safety group, there's costs in the engineering group, there's costs in the operating group. So what they've done is they've accumulated all these costs, and they were surprised to find out what it really costs to carry these old sites on the books. It's very useful for those of you who have these kinds of sites. It's useful to do that. And then if there's a way for you to maximize the redevelopment value of those sites, you're going to see that in either your own reuse or in the sale of the asset. Schedule, hard to say what schedule means, except that if you tell the stakeholders what a schedule is, it's good to stay on that schedule. If you're going to do it right away, or it really kind of takes 3 years to get through a decommissioning process from the time you start planning it until it's done. And then finally, quality is another goal. So I define quality as meeting stakeholder requirements, and requirements are different than wish lists or asks. Everybody's got an opinion. Some people are entitled to get what they feel like they need, but not everybody gets what they want. Okay, so there's different business models which can be, and a lot of times these are combined. So owners of these sites, they can retain them for their own reuse, either as generation or transmission. They can retrofit to comply with the various rules. They can sell for utility as sell to another utility or an IPP or a financial buyer as a going concern. There's some data points out in the market. Old coal plants are selling for somewhere between, something like $150,000 a megawatt. Old gas plants, $500,000 a megawatt. The new build prices for these units are, coal is $3 million a megawatt, and combined cycle gas turbines are, closer to $1 million a megawatt. You can sell a site for redevelopment or adaptive reuse. You can sell it for scrap value. And just a word of caution, when you sell it for scrap, that's exactly what you get. There's some people out in the marketplace will say, I can do it for no cash. I just want the scrap. I'll give you back a flat level site at the end of the day. And what has happened on more than one of these sites is they take the scrap and then they go into some form of default. Either they leave or they quit, they dissolve. It's not good for the community. It's not good for the utility. And then there's a scramble to say what happens next. Donations are okay. You get a tax write-off for the value, for the fair market value of the asset. And then there's one company, public company, who puts their assets in a particular state into bankruptcy, and then they auction them through the bankruptcy courts. And that has actually worked. I'm not sure if it's the best way to use the bankruptcy law, but it has worked in Connecticut and in New York State. Paying for it. So I'm spending a lot of, there's a lot of things that people would like to do, but in the absence of a return on investment or a legal compulsion to tear down plants, utilities are reluctant to invest the money. But there are ways to pay for this. So for transmission and distribution improvements that have to be done to maintain reliability after a plant is taken off the grid, you can capitalize those costs because most of the T&D systems are regulated utilities. There's asset sales, salvage, scrap and real estate. Salvage in an old coal plant, there's not much there. Scrap, somewhere between $5 and $15 million of copper and steel scrap. Real estate, it depends where it is and how big the site is. The New York City project we talked about, it was $680 million. If you have a small site in the middle of nowhere, it's not going to be worth, like I say, it depends on what you're going to do with it. Rate basing and regulated utilities. I am surprised that utilities who have power plants that they intend to close in regulated states, that they're not charging ahead with that, because they do have an opportunity to rate base those costs subject to the Public Service Commission. But we're not seeing that. Operating costs, the shareholders pay in deregulated utilities, IPPs, the shareholders bear the cost. There are reserve accounting issues. What we're seeing is that people have set up reserves for asbestos. They've set up reserves for coal ash. Not many companies have set up reserves for demolition costs. These costs can be material, and I'm not saying that these companies have gone into bankruptcy because of plants that they're closing, but Dynegy, Mission Energy, and now Energy Future Holdings have all gone into bankruptcy proceedings. Dynegy is out. Mission Energy was acquired by NRG. Energy Future Holdings is just started. Over in Europe, they have a little bit of a different problem, but in Europe, the thermal generators have been suffering because of subsidized renewables, and they have just in the past year taken some huge charges to write down the value of their assets. So I don't know whether that's going to happen here or not, but that's something to think about. So just to drill down into a little bit of detail, playbooks based on, these are TRC deliverables on power plant closure projects. Playbooks tend to be a $120,000 contract 2 or 3 months to execute based on existing information. We'll look at available asbestos and hazardous materials information. We'll look at transmission and other utility issues. We look at asset valuation, develop a matrix of permits that are required to close the site and or keep operating the site, depending on what you're interested in doing. A phase 1 environmental site assessment. We look to see whether there's any constraints on means and methods. And those constraints are, when a plant is being taken out of service, there's always 4 impacts. There's noise, dust, vibration, and trucks. So if any of those issues constrain means and methods, and the means and methods are you can blow it up, you can pull it over, or you can pick it with a crane, you may not be able to use all of those methods or on the entire site. So we look at constraints on means and methods. It always affects the price and the schedule. We look at community impacts, future use scenarios, which is always a very important thing to look at. And then if there's some realistic scenarios, we'll develop them into cost estimates and schedules so that you can make an informed decision about what to do next. And these kinds of packages are useful for groups like boards of directors or public service commissions so that they can see where the costs are coming from. Next level of detail is what we call engineering during decommissioning. There needs to be an asbestos survey. It's helpful to have a hazmat survey. If you don't do those things, you can assume that everything is asbestos and pay an abatement contractor to treat all the insulation as if it is asbestos. Or you can assume that nothing is asbestos and then pay for change orders when you find asbestos. So neither one of those things is really desirable. So we always recommend a thorough asbestos survey, hazmat survey, and we develop these things, and we develop a set of plans and specs for abatement and demolition. Give that to our clients as a bid package. And then going down the road, there does need to be some work plans. There are some permits that you need to get. And then we think it's always good to engage the community, tell them what's happening. They may not care, they may care a lot, but they like to be most communities like to be informed. And we do that through the use of fact sheets, websites, presentations. We think the putting information up on a website is really great for people who worry a lot. And if they want to know what's happening, they can just log in and find out. Some of our clients have extensive disadvantaged business enterprises and 30, 40%. I think California is up to 42% DBE requirements on contracts like this. So all that needs to be built into the procurement process. Construction support services, this is something the owners can do it. They can hire a contractor to help them with it, or they can do it together. But the kinds of, it's really difficult to just turn a site over to a demo contractor and let them have at it. They're going to do what's good for them. They may not do what's good for you. But project management, site management, contract administration, change management, health and safety inspections, environmental inspections, and at the end of the day, you may need a document package to record what was done on site, trucking manifests, air monitoring, asbestos monitoring, so on and so forth. Something else that needs to be done. And then asset recovery is the one issue that seems to consume more time than anything else during the bid process. And what we tell people to do is think about what you would pay for the salvage equipment that's available on site. And some of the equipment, air compressors, fire water pumps, house boilers, control systems, you know, if somebody, what would you pay for it if somebody else had it for sale? So the best market seems to be internal within the companies. If there's no market for this kind of equipment in-house, it's probably not going to be much of a market out in the marketplace. There are auction houses that I call them like garage sales, and people literally come in and I'll give you $5 for that set of spare, you know, that warehouse full of spare equipment. It's really a tough and frequently disappointing exercise. A lot of litigation with auction houses. Right now, scrap is about $400 a long ton. 500 megawatt power plant. You might get $10 million for the scrap. You might get 8, you might get 12. It depends on where the plant is. Is it closer to export markets? Is it closer to a mill? But it's a very significant amount of money. Copper is less predictable. A lot of copper gets lost in the process. This is a commodity market. If you want to know what the values are, you can get a subscription to either the American Metals Market or the London Metals Exchange Market. Some of the information is available in the Wall Street Journal, but you're better off getting a subscription to AMM. And then, who takes the risk on scrap value? If you lay it, you can, you know, the owner can take the risk, contractor can take the risk, or they can share the risk. If you sign a contract with a demolition contractor on July 1st of 2014, he's probably got 6 to 12 months of abatement. So he's really gambling on the steel markets in 2015 and 2016. So the way that they deal with that risk is they discount either the quantity or the value of the steel, and their bid price will reflect that risk adjustment. The other way you can do it is share the risk and with the contractor, and you share the upside. If you're sharing the downside, share the upside. I'm going to go through some projects, and I think we're okay on time. So this is an old slide that I've given many times in these kinds of presentations, but this is a Con Ed site in New York City. It was First Avenue, just south of the United Nations, to give you an idea of where it's located. So this was an MGP site, then it was a coal-fired power plant, then it was an oil-fired power plant, and finally it was converted to gas before it was closed in 2000. Well, it was closed. They were supposed to close it in 2003. They didn't close it until 2005. But it was actually two power plants, 3 million pounds an hour of steam. The photo on the upper left, you can see the MGP facilities on the right-hand side of that photograph. There was a 700,000-foot office building, 2 power plants, a 250,000-gallon underground oil tank, and then a vehicle service facility, which was the worst part of the whole job because of a leaky gas tank. But anyway, we got this site in 2001. We got the power plants in 2005. Everything was done by 2008. And there's been some development on the site. There's a school and a couple of apartment towers that are, the school is in session. The apartment towers are in construction. The other development has lagged, not for any particular reason. One of the other interesting things about this site is there were 7 intake and discharge tunnels, which were very deep, and the top of the tunnel was always below the level of the East River. So they were difficult to get out. We said, hey, we'll close them in place. They said, well, we want to build skyscrapers. We don't want to deal with these old tunnels, so take them out. So we took them out, but it was a tough, tough to get out tunnels that are underwater. Hunters Point and Humboldt Bay, San Francisco. Here again, these were oil-fired power plants. In California, there's always the dirtiest plant in California. Hunters Point is on the waterfront, part of a huge redevelopment zone. It was 400 megawatts. PG&E broke it up into pieces. above ground demo, below ground demo, and then cleanup. You can do that. It just takes longer. It costs more. So we were the prime on this. We did the engineering. We hired the subs. The project was done in 2010. And Humboldt Bay is up at the end of the line in Eureka, California. This was the this is a oil-fired plant and a nuclear plant. We did the thermal plant. They just awarded a contract for the nuclear side last year. I guess that's going to also be closed. No future use at this time, but the San Francisco site is part of a very, very large redevelopment area. Austin, Texas. So this was a plant, 500 megawatt power plant in the city of Austin in an environmental justice neighborhood. People have been trying to close this plant for many, many years. In 2007, Austin Energy is a municipal utility. They finally said, okay, we agree, we're going to close it. So we won this competition, and there were a lot of requirements. It's finished. It was finished the end of last year. The lesson on this plant is what happens if you have a bad asbestos survey, because containment went up, clearance was granted, containment came down, and then we peeled the skin off the boiler and found, guess what, lots of asbestos. So that created, there was a delay, there was a change order, but there's a need for thorough asbestos survey on these projects. Big DBE component, 38%. Contractors, they were all great. We're going to talk about Long Island is, of all places, kind of a laboratory for repowering. And right now there's 5 projects on the island in play in one form or another. So Far Rockaway is near JFK Airport. This is the upper left photo. The coal plant is down. There's 2 peakers. I suspect that there'll probably be some new plants built on this site, but not yet. Glenwood Landing, there were 200 megawatt towers and then these old Riley boilers in the brick building. We have on this side, this is under being demolished at this time. There's peregrine falcons, there's state historic preservation issues. Just because you say you want to do it doesn't mean you can go ahead and do it. You got to deal with all these ancillary issues that pop up. It's almost done. The driver on the Glenwood Landing site was property taxes, which were north of $20 million a year. Same thing on Barrett and Port Jeff, and for the time being, those taxes could be passed back into the rate base, but that was going to end. So there was a need to close these facilities and get them taken down on a time schedule. So neither Far Rock or Glenwood will be replaced at this time, but Barrett and Port Jeff are repowering sites. At Barrett, it's build a new one, take down the old one. At Port Jeff, it's take down the old one and then build a new one because there's no room for a new plant at this time. And these are just some progress photos. These LRD machines, long-reach demolition machines, are very useful. They're up to about 180 feet. It's a good way to use equipment, more equipment, less labor to take these plants down. It reduces the risk of an accident. And then there's Naipa Paletti. Naipa Paletti was sort of a bargaining chip. This is an 850 megawatt plant that Con Edison started to build in the 70s, sold it to the New York Power Authority, and then New York Power Authority is a state institution. Governor Pataki wanted a state-of-the-art, layer, air-cooled condensed, gas-fired combined cycle power plant, and the Enviros in New York State said, you want a new plant? Close the old plant. So there was an agreement struck to do that. The new plant's been up and running for quite some time, and whenever it's available, it just runs flat out. And Paletti is currently being demolished. Probably be done in the 4th quarter of this year.
Ed, in the interest of staying on schedule, if you could wrap, that would be
I'm done.
terrific.
I'm done.
Perfect.
Okay, Kenosha is 1 million feet under roof, redeveloped, and we'll skip that. And that's all I got. This is these are some other example projects. Anyway, if there's any questions, I'm happy to answer them, or a simulator, and we'll keep this show on schedule.
Thank you. Any questions?
I'll be here.
Looks like you'll get a question maybe at the break.
Okay, great.
All right.
Thank you.
Fair enough. Thank you, Ed. Our next presenter hails from my home state. William Wang is a research associate in the Department of Chemical and Biomolecular Engineering at The Ohio State University. He's going to talk to us today about chemical looping cycles for carbon capture, which we've heard a little bit about already, electricity generation and chemical production. So, William, if you'll take the podium, the floor is yours.
Okay, I believe, there we go. So chemical looping is an interesting technology. So this presentation will differ from all previous presentations because chemical looping is still most definitely a technology that's being developed, but every sign does show that it can lead to commercial scale demonstration operations. Currently, as all these chemical looping projects that are occurring throughout the world continue to scale up successfully, this chemical looping technology does have the ability to completely transform how fossil fuels are utilized. First, though, it's kind of important to take a global perspective of how energy is consumed. So if you take a look at this chart, it's very obvious, very clear that fossil fuels dominate our initial primary energy source. And given the current portfolio for energy being oil, natural gas, and coal comprising about 80%, 60%, 80%, sorry, 80%, it's very clear that for the near future, fossil fuels, carbonaceous fuels, will continue to dominate. The world is not decarbonizing our energy, and we aren't shifting towards renewables to any great extent. Now, I realize that CCS, CCUS, CCGS, CCUGS, whatever you want to call it, is not a viable option for reducing CO2 emissions in its current state due to economic challenges and difficulties. However, that doesn't mean that in the future it can't be or won't be as research continually develops and advances. So everyone here knows the purpose of CCS. Tom and Jordan did a fantastic job yesterday going over the details of what the DOE is doing in terms of CCS. But the overall strategy does require government regulation and technological advances in order for CCS to be viable. In terms of government regulation, everyone here, the US EPA mandates and proposals have been discussed in great detail. But internationally, the European Union has also set up the emissions trading system, or emissions trading system for CO2. I did steal this, in terms of technical advances, I did steal this. It's quite dated, but I did steal it from the DOE NETL, so if you guys want to prosecute me, you have every right to do so. But as you can see, chemical looping is here, and it does show that in terms of what the DOE believes, DOE NETL believes, is that chemical looping provides the greatest cost reduction benefit, although we do take issue that and believe that chemical looping is more somewhere in this time frame in terms of commercialization. So now, what is chemical looping? It's simply a cyclical process where a chemical reaction is divided into several subreactions using intermediates. There are two types. One is purely for CO2 removal, and the other one is the more interesting one where it uses a metal oxide carrier particle for oxidation reduction. In terms of CO2 capture, it's typically a metal carbonate, typically limestone. It's calcined, and then CO2, a pure stream of CO2, is emitted, while the metal oxide reacts with the CO2 and the flue gas to form the metal carbonate, and the cycle continues. In terms of the redox cycles, what happens is a metal oxide reacts with the fuel, and depending on the metal oxide composition, the reactor type, you can get a variety of products, including syngas at any hydrogen to CO ratio you want. You just need to play around with the particle. You need to play around with the fuels. But syngas, hydrogen to CO ratio at any desired fraction. You can get electricity through complete combustion. You can get hydrogen. You can get liquid fuels. It just depends on how you decide to set up your reactor system. And then what you can see is that it's just a complete redox cycle between the metal oxide and the reduced metal. The main benefits, there are several of them for chemical looping, is that it is an inherent CO2 capture technology. It's not, you don't need an amine scrubber, you don't need any back-end sort of CO2 removal system. It by itself is inherently a CO2 capture technology. It provides a highly efficient method for coal and natural gas utilization, where efficiencies can range between 50% and 80%, depending on what products you want. It's fuel flexible. We have, throughout research throughout the world, has tested biomass, coal, natural gas, lignite, pet coke. Everything has been tested. And then it's also product flexible, like I said earlier, where if you want syngas at any hydrogen to CO ratio you desire, it can be achieved. You can produce electricity and value-added chemicals. The challenge is the particle development. The greatest barrier and the number one failure for chemical looping systems is the particle. DuPont had a maleic anhydride chemical looping system, but it failed because their particle continued to, or over time, failed to continue to provide the oxygen, so they just eventually ended up using an ASU. The second one is a solid circulation, where obviously on the commercial scale, it's going to be on the order of thousands of tons per hour. Not impossible, but very difficult on solids management through attrition, particulate capture devices. Everything has to be maintained. And then obviously the last one is a process integration, and that leads directly and ties in directly with the process economics. The idea of chemical looping isn't a new idea. In the 1900s, the Lane and Messerschmitt process was actually a chemical looping system for hydrogen production, very similar to what we are using today for our hydrogen production as well in a chemical looping system. The first reaction, the top one, is simply the steam iron process. The bottom reaction is the reduction of Fe3O4 back to Fe using CO. The net reaction you can see is a water-gas shift reaction, but since you broke it into two intermediate reactions, there's no need for a water-gas shift catalyst. There's no need for breaking the equilibrium or trying to shift the equilibrium, because there is none. It's inherently performed through the chemical looping system. And then in the 1970s, Consol Energy had the CO2 acceptor process, and what they were trying to do was they were trying to use calcium oxide both as a CO2 carrier such that the water-gas shift reaction could could move in the forward direction. Plus, since it came from the calciner, which was at a higher temperature than the gasifier, the calcium oxide also provided heat to the gasifier as well. So again, there are two types of chemical looping systems. The first one is the for CO2 removal, and this has been studied heavily using carbonates, usually naturally occurring carbonates. RTI used sodium carbonate. The Europeans actually have scaled up their process to a 1.7 megawatt thermal in Hunosa, Spain, using just pure plain limestone, not doped or anything, just limestone from the ground. And what we do at Ohio State is we actually use calcium hydroxide, so we provide an intermediate reaction step to convert the calcium oxide to calcium hydroxide, and I'll go into that a little more later. Additional solids include hydrotalcites, and magnesium hydroxide as well has been studied. So at Ohio State, we have chosen calcium hydroxide because what we've noticed is that calcium hydroxide is far more reactive than calcium oxide over multiple cycles. Calcium oxide is known to degrade in cyclical fashions for CO2 capture, while calcium hydroxide has shown a steady CO2 removal. So it's a three-step process, 3 reactions, all at high temperature. The calciner is where everything starts to form the calcium oxide. That is then hydrated under using steam around 500 C, which is an exothermic reaction. So quite a bit of heat is provided through the hydrator at 500 C. And then in the carbonator, that's where the CO2 capture occurs, and then it continues in a cyclical fashion. We demonstrated this at the 120 kilowatt thermal scale at Ohio State using a coal-fired stoker donated by Babcock and Wilcox, and using direct injection of calcium hydroxide and several other oxides into our flue gas to see the removals. This is the stoker grade Ohio coal, and this is the coal flame. The single cycle studies were very successful. Calcium hydroxide showed great promise. So this was the cyclical setup where solids were injected up here and then just continued through the cycle. And this is our rotary calciner for calcination. What we were able to achieve is 90% CO2 removal at a calcium to carbon mole ratio of 1.3. This can be compared to natural limestone tested by the Europeans, where they need a 10-to-1 calcium to carbon mole ratio for 90% CO2 removal. Because of the high calcium to carbon mole ratio and the carbon to sulfur ratios, we get 100% SO2 removals using calcium hydroxide, even though we're at temperatures far lower than furnace sorbent injection, and that's just because the calcium to sulfur ratio is at least 50-to-1. In the carbonator, the residence time is on the order of seconds to achieve the 90% CO2 removal, and we've been able to sustain the reaction for several cycles. This is just a simplified process flow diagram of what is circulating through the system and the energy inputs and outputs. I like to call this slide what I did over the summer. In order to see what the effect of process parameters on the carbon capture process, the CCR process as we call it, is in terms of energy penalty, in terms of materials consumption. I started out with case 11 of the DOE baseline report. So this is the coal-fired boiler here. I apologize. I had to break this up, and it's still incredibly small. Coal and air are fed into here, and then flue gas comes out. This is the steam turbine cycle. Again, this is for the supercritical case, case 11, along with using the QGESS standards put forth by the DOE. And then up here is the actual carbon capture where the flue gas comes in. And then this is the CO2 compression. This is the calciner, which operates in an oxycombustion mode. And that was per the standards of the oxycombustion report, again, put forth by the DOE, as oxycombustion calciners haven't really been developed yet. And then the hydration obtains steam from the intermediate pressure and low pressure interchange. So the advantages of using this high temperature carbon capture process is that it uses limestone, which is about $25 a ton, very cheap if you get it closer to the mine. Because of the high calcium to carbon mole ratio of 1.3 to 1, our simulations show, we haven't formally demonstrated it, but all acid gases are removed, SO2, SO3, HCl, and that's just because of the trace amounts that are present and the high amounts of calcium circulating through the system. The process integration is flexible, where you can use either high temperature or low temperature flue gas. You can take steam from either the intermediate pressure, low pressure interchange, and if vacuum compression or vacuum heat exchangers are developed better, you can also take it from the exit of the low pressure steam turbine, but it is under vacuum at that point. The energy penalty, steam consumption, and oxygen consumption are all lower than amine scrubbing and oxycombustion. Under the very worst case scenario, the energy penalty is around 25%. It's usually lower, 15 to 20%, 15 to 25%. And that's again because of the amount of high pressure or high temperature heat available through hydration, the heat of reaction for hydration, and the cooling of the flue gas from the carbonator coming out at 625 C down to stack temperatures. The second type of calcium process is a pre-combustion one, where the calcium hydroxide now actually serves two purposes. One, it actually provides the steam for the water-gas shift reaction upon decomposition. And second, it breaks equilibrium by capturing the CO2 and driving the reaction forward. Under the correct operating conditions, no catalyst is actually necessary to obtain high kinetics and high conversions to hydrogen. That is the only difference. The calciner and hydrator remain the same. It is also a process intensification, where this is a typical calcium looping process, or calcium, not calcium, but IGCC process, where you can see all this is necessary, but because of the reactivity of the calcium hydroxide, it's reduced to this, where the calcium looping process, the three-reactor system, replaces everything here. Consol Energy did an independent, with our input, did an independent Aspen simulation and economic analysis, and they also had to make a lot of additional assumptions because they were producing so much extra electricity, they didn't know how to handle that. So the total first-year cost of electricity is about $92 per megawatt hour, as opposed to the coal-to-hydrogen-based plant. And it is the lowest cost route for hydrogen production with CO2 capture is steam methane reforming plus the CLP process. Now, the more flexible and the more interesting, probably, type of chemical looping is the redox one, where you have a metal oxide reacting in a cyclical loop, becoming metal oxide and metal. And this is just a schematic where you can see the metal oxide metal oxide enters, and then the reduced metal exits. There should be an O here. And basically, like I said, you can produce your syngas, you can produce complete combustion products, you can produce chemicals. And what you can see over here is it's still combustion, it's just that the nitrogen is over here and the CO2 is over here, so there's no dilution of the CO2. It's inherently a CO2 capture process. Again, the most critical factor for success to chemical looping is the metal oxide. The initial composition is based on thermodynamics, and then you have to go into kinetics. But what's also interesting is there is a subset of metal oxides, such as the copper oxides, that upon heating will provide gaseous oxygen, as opposed to iron oxide, which remains lattice oxygen donation. So depending on if you need gaseous oxygen or lattice oxygen, you have to make your choice there. Additional considerations are environmental health effects, cyclic reactivity, strength. So initially, the method for determining what particle to use for the metal oxide was done through trial and error, where they would just take a metal oxide, test it, see if it works. If it didn't work, they would tweak it, maybe add some additives, maybe go to a different one. Now things are becoming more scientific, where they are looking at reaction mechanisms and using density functional theory to actually determine the type of metal oxide to produce. It's becoming more of a catalytic science than it is a trial and error, which is quite positive. So far, iron, nickel, copper, manganese, and cobalt are the most common types of metal oxides. And you can also go with naturally occurring metal oxides such as ilmenite, olivine, or you can also make your own, such as iron oxide doped with something, or any metal oxide. This is version 0.0 of our syngas chemical looping unit. It's 25 kilowatts thermal, located at Ohio State University. It has since received significant upgrades. So this is just showing, again, the idea of chemical looping, where this is syngas combustion to form CO2 and H2O, but it's done in such a manner that the iron oxide does the transfer between Fe2O3 and Fe. We have tested over 300 hours of operation using all types of fuels, gaseous fuels. We've done methane, we've done natural gas, we've done syngas. What's interesting is also, because we use iron oxide, from Fe, you can go to Fe3O4 using the steam-iron reaction to produce hydrogen, and then do a dual-step oxidation from Fe3O4 to Fe2O3 using air. So this chemical looping has the ability to produce hydrogen as well. High gas conversions, high hydrogen purities, high solids conversion. And this is the process that has been chosen by ARPA-E to be scaled up at the National Carbon Capture Center in Wilsonville, Alabama. It's currently actually undergoing demonstration as we speak. We also have another chemical looping-based system called coal direct chemical looping, and that takes coal, reacts it with the iron oxide. Again, you can form carbon monoxide, you can generate your syngas, you can generate your hydrogen, you can generate your electricity. And we have been able to successfully demonstrate this actually for 10 continuous days, over 300 hours of, for 10 continuous, 200 hours, sorry, it's this one, 200 continuous hours with absolutely no issues in terms of solid circulation, in terms of conversion, in terms of operations. We were able to do it for 200 hours continuous in the fully integrated unit. We have tested coal, biomass, petcoke, lignite, PRB. Everything is fully functional. There have been no operational issues. And this has the ability, again, to use coal. So this idea of retiring coal plants, there are alternatives that do exist with encouraging preliminary economics. Of course, further testing is always necessary. Again, Consol Energy has done their own independent economic analysis, starting with their own Aspen simulations using our experimental data. And as you can see, the base plant is about 58.9. CDCL plant is about 78.4. It's less than a 35 increase in cost of electricity for preliminary economic analysis. And what's really encouraging is that the energy penalty is only 10.5%. In terms of additional chemical looping systems that are occurring throughout the world, this is the 1.7 megawatt thermal post-combustion CO2 capture using calcium oxide in Tolosa, Spain, but also Darmstadt University, ITRI, Alstom. They also have all large-scale demonstrations occurring as well. And then, in addition, you have universities such as University of Kentucky, University of Utah. You have private companies also looking at chemical looping cycles. So this is actually, all the results to date are actually very encouraging for continued fossil fuel utilization and transformations in ways that are far from traditional. Thank you.
Thank you, William. Any questions from the audience? Going once? Going twice? All right. Thank you. With that, I would like to invite Richard Mimna, Senior Research Associate at Calgon Carbon, to come up and offer the next presentation on activated carbons for challenging situations. I think we heard a few examples of some of those challenging situations this morning, so I'm very much looking forward to your comments. The floor is yours.
Thank you.
You bet.
All right. Well, good morning, everyone. Thanks for being here. And as the title states, I'd like to talk to you today about the use of activated carbon for mercury control in challenging situations. Okay? So I understand, I guess I have a full half hour to bore you with here today, and I think I have a slightly mixed audience. So I thought for a change I'd start with a little bit of Carbon 101, if you will, because it's something I don't see discussed a lot in presentations. Basically, the high-level view of what is carbon, how does it work, how do we make it, and so forth. But then from there I'll transition into talking about activated carbon for mercury control, but more specifically applying activated carbon in situations that traditionally have been impossible for activated carbon. Situations that include the presence of SO3, for example, situations where you want to preserve the quality of the fly ash for sale to the cement market, and also situations where DSI for SO2 has to be done in conjunction with ACI. That can cause some interference. I'll be illustrating this with, of course, some data with some Calgon carbon products. I'm not here to try and really give you a sales pitch or a commercial. The takeaway I want you to have from this presentation today is that those hurdles that I have listed here traditionally have prevented the use of activated carbon in many situations, but thanks to advancements in the field, those really are being overcome today. Okay. So, believe it or not, activated carbon has over 600 applications, and we service many of those. At Calgon, we're fond of saying that activated carbon is even more useful than duct tape. I think if we could find a way to combine carbon and duct tape, we might really be onto something there. But some of the applications are listed and depicted here. That includes industrial VOCs, agriculture, disinfection byproducts, and so forth. I've got a sort of amusing one here in the bottom right that I've shared before. This is sort of an odor control application, if you will. I keep saying to our sales guys, I think we should hand these out at our booth at conferences. I think it would generate a lot of buzz, but they keep ignoring me. So I guess I'll stick to R&D and let them handle the sales stuff. So what is activated carbon? It's fair to say that it's largely graphitic in nature. What is graphite? Well, let me back up a step further. Sort of a buzzword in science these days you may have been hearing about is something called graphene. This is a single atom thick layer of carbon atoms in which all the carbons are arranged in the hexagonal pattern that you see here. What drives graphene researchers crazy is that those layers don't like to be single layers. Rather, they like to stack up one atop the other in a very, very ordered and very stable fashion. And when they do, that's when you get graphite. And graphite is found in everything from carbon pencil leads to fighter jets. Now, activated carbon is graphitic in nature, but instead of that high degree of order that you have in graphite, it's as if you took those stacked layers and then dropped them. It's like, say, taking a deck of playing cards and dropping it into a hat. Or another analogy is to look at a jar of peanut brittle. You have all these disorganized and jumbled plates fitted together, and it's that disorganization that creates the porosity that makes activated carbon so useful. Okay. In fact, you can find up to 1 million-fold ranges in size as far as the pores go, all the way from visible cracks and granules down to the microscopic. The old timers back at Calgon Carbon like to argue that activated carbon is the original nanotech. I'm not sure that I agree with them on that point, but I get where they're coming from. However, when it comes to adsorption, it's really only the smallest 5-fold range of pore sizes that do the work, that do the adsorption. Okay. There are some pores that do the adsorption, and then there are larger ones that help transport through the particle, or through the granule, if you will, to get to those adsorption pores. Here again, to use some analogies, sometimes we like to compare it to the highway system, where your large interstates and your highways are your transport pores. You come off to smaller side roads, which are your finer transport pores, and eventually wind up at your driveways, which would compare to your adsorption pores. Or another analogy is the hotel, where you walk into the large lobby and then go down smaller halls and eventually wind up with all your hotel rooms, which again are your adsorption pores. Okay. So when it comes to activated carbon, you'll hear terms thrown around like adsorption and absorption. It can be a little confusing. When it comes to activated carbon, what's going on here is adsorption. Okay, that means when something is picked up by activated carbon, it's sticking to the activated carbon, as you see in this diagram here. That's in contrast to the absorption process, whereby a sorbent would actually take something within itself and consequently it would swell. And there are sorbents that do that. For instance, there are some clays that will adsorb in that manner and actually swell. Okay. Here's just another picture to help you visualize what's going on here. If you will, these would be particles or granules of activated carbon, and then your disordered graphitic plates. Okay. So activated carbon can be made from quite a wide variety of starting materials. All you need is something very, very carbonaceous to start with. That could be coal, it could be tires, it could even be chicken poop. All right. However, the material that you start with is going to dictate the final properties in your final product. The ash impurities are inherited. Density and hardness of your product are closely linked to the starting material. Of course, your overall porosities depend on starting materials a lot. And really, each starting material gives you a unique class of products. So that in the end, what you make from bituminous coal is not the same as what you make from lignite coal or coconuts or wood or what have you. Okay, we'll talk a little bit more about that later. How do we make activated carbon? In a nutshell, there are 3 different ways to do it. At Calgon Carbon, because we use bituminous coals, we rely on a process we call reagglomeration. And that involves a thermal activation at the end step. You can skip the agglomeration step and do what's called direct activation. That's also a thermally based activation. And then thirdly, there's also chemical activation, but something I won't really delve into today. Here's a depiction of those 2 different processes, though, reagglomerated and direct activation. On the top, we have the reagglomerated depicted. What we'll typically do is we'll take usually a blend of coals, bituminous coals, and we'll crush them up in the pulverizer. And then we'll actually take that crushed coal and we'll glue it back together. We do that with a petroleum-based pitch product. And then we go and we smash it again, which seems utterly counterintuitive, right? But there's actually a good reason for that. What happens to that pitch in the next step, in the baking, is that it breaks down and volatilizes away. And in doing so, you've artificially now created transport pore structure in your activated carbon. Okay? By contrast, with direct activation, they skip this reagglomeration step. And in certain cases, depending on your starting materials, you can even skip the baking step and go straight to the activator. And then in the end, you come out with this nice black product. We have this horrible joke in the activated carbon industry that we can make carbon in any color you like as long as it's black. Right? But what you have is a granular product, all the VM driven out, very, very high surface area and porosity, and very, very inert material. I understand it was stated yesterday that there's a risk of explosivity with activated carbon. Can activated carbon be explosive? Yes, it can. However, even my shoes could be made to be explosive, right? Anything that can potentially combust at all, given the right conditions and enough energy input, can be made to explode. But practically speaking, is activated carbon an explosion concern? No, it is not. We've been submitting samples of activated carbon to experts in the explosivity testing industry for decades now. The KST values that come back, that's the best value for comparing the inherent explosivity of one powder to another. That KST value consistently comes back at under 100, which puts it in the weak explosion category, which puts it on par with something like powdered milk. Personally, I wouldn't be afraid to have a silo of powdered milk on my site. And furthermore, recall that powdered carbon has been used to treat flue gas for decades now, since the 1990s at least, in both North America and Europe. And to my knowledge, there's never been an explosion of virgin powder activated carbon. And if you think about it, activated carbon is much like charcoal. Has anybody here cooked with charcoal before? Do you put a match to it to light it? It takes a little more than that. You have to put on the lighter fluid. In effect, you're adding the VM back that you drove out in the first place so you can get the stuff to burn. And furthermore, when it does burn, it doesn't go